We're covering classifications or types of bones just based on their shape. And we did this with other types of tissue. Remember, there's 4 types of tissue in the body: epithelial, connective, muscle, and nervous. And we look at connective tissue, there's 3 types: connective tissue proper, we learned connective tissue fluid, and now supporting, and supporting includes our cartilage and bone. So we're on to bone now, but we start by just naming how do we describe them and compare them to others based on their shape or type. We started to do this with epithelial tissue because we named based on cell layer and the shape of the cells. Remember, we talked about cuboidal, columnar. So we do the same thing with bones because we try to compare them, especially when we start to learn how they grow and how they develop through osteogenesis and bone development, which is ossification. So our classification of types of bone. Simply put, one is long relative to another one is short. So we're comparing them relative to other bones. So our long bones include things like the femur, the humerus, the tibia, the fibula, relative to bones like the tarsals, and here are the carpals. So there's 8 carpals here that we'll come back to naming them in a future video, but these are short bones relative to the long ones. So you have short bones. And then we get into things like flat bones. So flat bones, I showed 2 examples here. First, the sternum is a flat bone. This bone takes about 20-25 years for it to completely all fuse together. And then we have our ribs. We have different types of ribs. We have true and false and floating. And they curve, but relative to other bones, they're still flat. So they may curve, but relative to a long and a short, they're flatter bones. Okay. And then irregular, they're all over the place. Some of my facial bones, so my face is irregular, and my vertebrae. So this is stacking 3 vertebrae here, but they're not long, they're not short, they're not flat, they're kind of all over the place, so we call them irregular. And then sesamoid bone. The primary example any text will give for a sesamoid bone is the patella. And sesamoid bone means sesame, like it looks like a sesame seed. And this is looking at the kneecap or patella. And it's going to be surrounded by other types of tissue. So I'll have other connective tissues in our connective tissue proper that will cover over the top of this. So it's actually embedded in other types of tissue. This makes it a sesamoid bone. We see this also in our hands and our feet, but the primary example is going to be your patella. And then sutural bone. So I have dense fibrous tissue that helps connect all of my cranial bones. And when I look at facial, we'll come back to sutures as well. But there's sutural, and it's the boundaries of each of these bones as they come together and fuse. And so later videos, we'll talk about fontanelles and how we see those early on in development. And then sutures. And suture bones are just these tiny little fragments that help create the actual skull or cranium. And these connections we'll learn as we describe how the bone develops and comes together. So sutural bones. And then lastly, pneumatized bone. Some texts don't talk about pneumatized bone, but this is an example of the ethmoid bone. So the ethmoid bone comes right in top of my nose, and it'll show up on the inside the cranial floor when I open up the cranium. But a pneumatized is essentially, it's an irregular bone, but the difference is it has a lot of air sacs to it. And this helps with like our sinuses and draining when we think about just getting into our nasal cavity. But we also use it to breathe. So as air goes through the different holes that we'll describe with the ethmoid bone, it helps us stimulate the olfactory nerve, cranial nerve number 1, for olfaction or smell. So pneumatized by definition, meaning it has more air sacs to it. We'll see in other types of bones, the temporal bone has a landmark called the mastoid process. That has air sacs to it. So it's unique in the sense on how it's developed. So I have long, short, flat, irregular, sesamoid, sutural, and pneumatized. These are shapes, and we describe them as classifications of bones or types of bones. And now later in the next video, we'll talk about the makeup of bone. How do we get to this point where we see these types? We're covering the makeup of bone. How do we actually create a bone? Later, we'll talk about growth and development, but we start out with what are the actual cells that give me the tissue that we see? Remember, there's 4 types of tissue. And when we look at connective tissue, we said it's specialized cells that make a matrix. When we learned epithelial tissue, we described one of their characteristics as cellularity with tightly bunched cells, not much material in between. relative to the other tissues. When we cover connective tissue and look at bones, now we have cells that become specialized because they're making a matrix. Remember, a matrix includes two things, protein fibers and ground substance. So we're describing this. When we look at the cells of bone, it only accounts sometimes up to 2 to 3% of all of the tissue. The rest is what it makes, which is the matrix. And then we have a balance of some cells that help to create a homeostatic balance during repair and building the bone as we grow up to 25 years old. So let's cover these cells, starting with mesenchyme or mesenchymal tissue. Mesenchymal cells are the basic embryonic stem cells for which all connective tissue will arise. So anything from our dense, regular connective tissue to our cartilage, we start out with mesenchymal tissue. We have a basic starting point. So these are the embryonic stem cells. Once we learn that we're turning into bone, meaning there's markers in the DNA that will be activated to say we're going to be at this place, we're creating bone, mesenchymal tissues will then turn into the specialized cells that make bone. So we start with the stem cells called osteoprogenitor cells. So mesenchymal cells turn into osteoprogenitor cells. Remember the key term of differentiation, that cells change over time. No different than you change over time. You go from a baby to a child to a teenager to an adult, and you change as you get older, but it's still you. So mesenchymal will change into osteoprogenitor cells. These are now the stem cells of bone. So we now mature to where we get to the point where we're going to start going through mitosis. Osteoprogenitor cells keep dividing, and eventually will then turn into the cells that actually do the work. So osteoprogenitor cells are still stem cells, but they're specific to bone. They will turn into osteoblasts. Osteoblasts are the young cells, the baby cells for B in blast, B for baby. Osteoblasts are the ones that are going to secrete the matrix. So they're actively doing something and creating the foundation. To me, it's like creating the house. It's the people that live in the house that are building it. There's only a couple of people live in the big house that they're building. Remember, we said bone cells account for only sometimes 2 to 3% of all the bone, depending on the bone. Osteoblasts get older and become osteocytes, and they help maintain the matrix. Remember, osteoblasts, as they get older and they become cytes, they now form that bubble around it called a lacunae. So osteocytes and lacunae. So now you have two cells. The younger cells secrete the matrix. Osteocytes are the ones that help maintain it. Now we finally get to the point to where all that differentiation occurred and you have actual bone material. Now I put this in red for osteoclasts. Osteoclasts come from what we call macrophages. Remember, leukocytes are white blood cells. These are macrophages. Macrophages engulf and eat things. And so osteoclasts with the C, what they do is they break down bone, which is helpful when I break a bone and help to repair and remodel it. So in theory, it goes back to the same shape. Remember in a previous video, we talked about long, short, irregular, flat, the types of bone. So based on the DNA, it knows how to regrow it to the same shape. And when we look at osteoclasts, they help for, as the bone develops over time, when my bone grows, it's getting bigger and bigger. So if I think about my femur, the biggest bone in the body, when I go from 10 years old to 20 years old, it's increasing dramatically in size. To help support the bone, I got to make sure there's enough inside material to make it function. So the diameter will increase, but then I have to allow room for it to develop. So osteoclasts will help create that room. And specifically, they're breaking down the inside to allow more structural support. So intuitively, that seems off. But if I'm going to build the house and I keep adding the walls to it, I'm going to need to do more inside the house and specifically give me more room for it to function. If the body needs calcium, osteoclasts will break down some of the bone to demineralize it and take some of that calcium and put it in the bloodstream. So osteoclast is a homeostatic balance, and it helps us to create the bones, remodel it, provide that calcium in the body when needed. And so we're finally at that point where we create that balance, and let's get into the matrix. So the matrix, remember, is made by osteoblasts. So osteoblasts secrete the matrix. Our matrix includes two things, protein fibers and ground substance. Protein fibers, 3 types: collagen, elastic, and reticular. Up to a third of all of the matrixes, including our collagen fibers. Remember, collagen fibers are the most abundant and they're the strongest to give us tensile strength. So these protein fibers help with that supportive flexibility. And then the ground substance is the material. Remember, it could be a fluid, it could be gelatinous, it can be hard. In this case, it's hard like bone. Calcium is our primary mineral that we use. Calcium phosphate and calcium carbonate are the primary compounds that we see in bone. Phosphate is a strong material that helps with compression. We see phosphate in the enamel of our teeth. Calcium phosphate is one of the hardest materials in our body because it's got to support that compression. If you think about my teeth, as I'm constantly chewing, it supports that compression as I squeeze onto my carrot that I'm eating. Calcium carbonate is similar to what's in an egg. So when you think about an egg, it's got a lot of calcium carbonate to it. So we see other species were similar in structure and function in how we do things. So I have the fibers that provide that flexibility, ground substance to help support that compression. So all of this contains majority of what you see in bone. And the body can keep rebuilding it. Remember, we said that in epithelial tissue, we said it does the most regeneration, that I keep rebuilding this over and over again. All of my epidermis can regrow in a month. Bones still grow and repair itself, and we know that when we break our bone. But a lot of our skeleton is completely remodeled and replaced every 7 to 10 years, depending on your health status, genetics. But as I get older, that'll slow down. But we keep rebuilding it to create that strength because it's the structural support of our body. This is the makeup of bone. We're covering bone regions and structures, and specifically doing this from a long bone. And this long bone that I have in this picture is a humerus. And we'll start with just the basic regions. And so a lot of it just understanding the terminology as we describe some different areas and structures of the bone. We have regions at the ends called the epiphysis. Plural is epiphyses, so ES. So epiphysis is the regions where we have the ends of the bones. And then I notice I put proximal and distal because we use our directional terms to understand where it's connecting. Remember, proximal is closest to that attachment point, distal is furthest away. In the middle, I have the shaft or the diaphysis, which is the majority of the long bone. What I don't have listed here, and some texts don't talk about too much, is the metaphysis. So if you notice here, I put a little gap here, but this is the metaphysis. And metaphysis is where we have this epiphyseal plate. Epiphyseal plate is where I have that growth. When we talk about ossifications, there's 2 types of bone development, intramembranous and endochondral. Endochondral means within cartilage, and we'll come back to that in a later video. But endochondral is where I have this strip of hyaline cartilage. As the bone is developing, we're stacking hyaline cartilage plates together. That's called the epiphyseal plate. When it's done growing, it forms bone, and then it's called the epiphyseal line. So it's the same thing, a line and plate. It just depends on the point of development. So that's where the metaphysis is. You may also see the term surgical neck, that the neck here is called the surgical neck, referring to from the medical side of breaking a bone. So we have our regions, our plates, and then when we look at the type of tissue for bone, osseous tissue is spongy and compact. In the epiphyses, I tend to see more spongy bone. So the type of tissue in this region of the epiphysis is spongy bone, and it's spongy because it's porous. And I may not be able to see through it, but it's got holes to it. Just like the sponge on the kitchen sink that you have. I can't see through the sponge, but I know water is going to go through it. Same thing with bone. One of our primary functions is blood formation. So we'll see blood fill within these spaces or pores of the spongy bone. Versus as I come down towards the diaphysis, I see more compact bone. So compact bone gives us that compression strength as we use the bone for our movement and leverage. So 2 types of tissue. And then when we look at the outside of the bone, the outside layer of this fibrous connective tissue is called the periosteum. Peri towards the periphery, osteum referring to bone. So it's the outside layer of the bone. As it's developing, we call it perichondrium because we'll see cartilage turn into bone. So periosteum is the outside lining. What I don't have listed here is endosteum. Endosteum is the tissue that'll line everything inside the bone. And we'll come back to that when we do histology, a spongy bone. So I have three regions, epiphysis, diaphysis, and metaphysis. And then we talk about two layers that help create it, periosteum on the outside, endosteum on the inside. And then I have spongy bone and compact bone, two types of tissue. We see blood inside the spongy bone. Within this space of the diaphysis, it's called the medullary cavity or the marrow cavity. And that marrow cavity is our yellow bone marrow. So it's yellow for a reason, because it's made up of adipose tissue or lipids. So it's energy supply as we need it. So within the shaft, I see fat, adipose tissue. Within the epiphysis, I see blood. So I use this a way not only to support the bone, but also support the body if it's needed. And then lastly, when I look on the outside here, it's showing nutrient arteries. So I have arteries that help to attach to the periosteum. And this is helping to feed the bone. We're taking blood out of it, but also during growth and development, we bring in these supplies. Because remember, bones can reproduce themselves and regenerate not as fast as other tissues, but roughly every 7 to 10 years. This whole bone will be redone over and over again throughout your lifetime if you live long enough. On the top here, I have what's called articular cartilage. So we'll see articular cartilage. Remember, three types of cartilage: hyaline, elastic, and fibrocartilage. This is hyaline cartilage. Hyaline cartilage is one of our weaker cartilage for strength, but it provides a lot of good support during movement, so I can move my shoulder over and over again. And remember, cartilage doesn't have a blood supply, it doesn't have a nerve supply, so it makes it easy as I'm using it when I have a bone that's constantly in motion over the period of my lifetime. So articular cartilage is hyaline cartilage. So we have our regions, we have our type of tissues, compact and spongy. We have layers, periosteum, endosteum. So a lot of it's understanding our terminology as we learn these structures and regions of a long bone. There's two types of bone, or osseous tissue: spongy bone and compact bone. How do we get to this point? There's four types of tissue in the body: epithelial, connective, muscle, and nervous. When we look at connective tissue, there's three types of connective tissue. Connective tissue proper, we have three types of dense and three types of loose. Connective tissue fluid, which is my blood and my lymph, and then connective tissue that's supporting. So our supporting connective tissue is cartilage and bone. Three types of cartilage: elastic, hyaline, and fibrocartilage. Now we're looking at bone. Two specific types: spongy and compact. They tell you what they are by their appearance. Spongy is spongy like the sponge on your sink when you're washing dishes, that it's porous, that it allows something to go through it. I can't see through it, but I know the water and the soap will go through it, and that's similar to what we see blood in bones, that we fill this area with blood. Versus compact is now solid, more like the wall to give me the structural support. So it's more densely packed cells. When we look at the model here, this is referring to an osteon model, and then it's got spongy bone to it. So as we look at the outer cover, remember that dense fibrous connective tissue is the periosteum. So this is the outside of the bone, the periosteum. And as I move inward, then we're looking at compact bone. So this is all compact. And then once it gets to where it's more like appearance of a sponge, this is spongy bone. So let's first look at the compact bone. When I look at compact bone, it's organized into a bunch of functional units that we call an osteon. So each of these circles and circles within circles are called osteons. And you can see when I pull one up and it's going the length of a long bone, that the way the fibers move is it crosses this way and then it twists this way and this twists this way. So that complementary structure, how it changes every circle within it, the direction it's going, gives me that shock compression strength for the bone. So when I look at one osteon, what we're showing here is it's got a middle section here to where I have blood supply, lymph supply, nerve supply. This is called the central canal or Haversian canal. So it's bringing in all the supplies. So on the side here, they're showing one that's opened up because we're constantly using this for blood formation and moving materials throughout our body. Bones are very useful for structure support, but there's a lot of things that are moving in and out. So when I look at the central canal, then it expands out, and you can see it's a circle within a circle within a circle within a circle. Those are called concentric lamellae, and it's basically how they've been building, and they'll circle around each other with the blood supply to keep forming those circles. This gives me an osteon, and the cells around it, what I try to indicate with those dark dots, are the osteocytes that would be in a bubble called the lacunae. And the way they interconnect are these little lines here, and these little lines are called canaliculi, little canals, canaliculi, that help connect cell to cell. So it's that communication point where we can expand and use this as a way to move materials. And when I look on the sides, you can see the strength, what's left over from building my osteons. These lines are called interstitial lamellae, So it's the way it's been formed to give me the structural support for compact bone. When I pull over and look at the slide, when I look at this is one nice central canal, that dark dot in the center, central canal, central canal. So those are indicating my osteon. So if I look at one osteon, it's got a circle within a circle within a circle within a circle. Hard to see it on the histology, but some are better if we go on a higher magnification. But I can see almost like it looks like a tree trunk or a dartboard to where it's just a circle within a circle. These dark dots that circle around, these are all my osteocytes and the lacunae. And they're connected with all these faint lines, and they look like eyelashes or sun rays, but they're real faint through here, and these are all the canaliculi. And as I create these circles, these are concentric lamellae. I put all these osteons together, and I'm getting compact bone. Versus when we pull over to spongy bone we tend to see more in the epiphysis, and compact bone we see more in the diaphysis for that strength. So spongy bone is porous. So if I show on this slide here, it's these pinkish rivers here. And it's a lower magnification, but I'm looking at the spongy nature of it. The darker purple inside is some of our blood, or blood marrow, or red bone marrow that fills in those spaces. Just like I talked about the sponge at your sink, that we're filling those spaces for a reason. So when I look at the lighter pink rivers, this is all spongy bone that's been formed. So if we went on a higher magnification, in the middle, I would see osteocytes, and they would be in the lacunae, the bubble that houses them. Towards the edge of the tissue, I'm going to see more osteoblasts because they're contributing to the formation of all of these structures that we call trabeculae. So I have osteoblasts, the cells towards the edge. In the middle, I know we have to go on a higher magnification to see that, but the cells, the tiny little dots through here, these are osteocytes in the middle. They're helping to form the spicules, which are the little struts that give me trabeculae, which is the functional piece of spongy bone. So all of these little pieces are these pink pieces here. So the difference between spongy and compact is not a location, same chemical composition, it's just how they're created and developed. So when I see my tree trunks, I know I'm looking at compact bone. When I see these pink rivers with the blood in between, I know I'm looking at spongy bone, two types of osseous tissue. We're covering bone development, or ossifications, as we learn how we get to understand our matrix of bone and we develop bone. There's two types of ossification, which is a bone development: intramembranous and endochondral. We're just going to describe the difference between the two, and then we'll have more videos talking about them independently. But when bone forms, that's called osteogenesis, which is bone formation. And then once it forms, it can start to grow. And we grow bones in two ways: in width, which is apositional growth, and then in length, which is interstitial growth. But we can't grow until we have the materials to develop it so it can grow. To me, bone development is this process of ossification. We bring in the right materials, which means the right cells, to then create the right matrix to give us what we need to develop bone. Because remember, bone is only sometimes 2 to 3% of cells. It's what they develop and make to form the bone that creates the actual product that you see as a bone. So two types of ossification: intramembranous and endochondral. intramembranous is referring to within a membrane, and we refer to this for dermal bones. We say dermal, like closer to the skin. So it's bones that I can, when I think about intramembranous, it's what I can feel. So I can feel my mandible. I can feel my frontal bone, my parietal bone. Those are bones that I can actually touch and feel. My clavicle, the right at the skin, dermal bones. And we call intramembranous ossification within membranes, and we'll talk about those membranes, but it's referring to these types of dermal bones. More of a simpler process of bone development versus endochondral is within cartilage, and specifically it's hyaline cartilage that we use it as a model. And what happens is when we talk about ossification, the actual definition is taking one tissue and replacing it with another. In intramembranous, we take mesenchymal tissue and turn it into bone, and we use the cells to make bone, osteoblasts, and then our osteocytes to maintain it. When we look at endochondral, we're taking first mesenchymal tissue and then turn it into hyaline cartilage to create a building block to then turn that into bone. And this can take years in many cases, depending on the bone. Somewhere it's up to 25 years for endochondral, usually referring to long bones. So as we look at this, let's just talk about when we talk about intramembranous. The picture here is matching the microscope slide down here, but what we're basically saying is I have a top sheet of mesenchymal tissue and then a bottom sheet. So it's in between two sheets of tissue. Remember, mesenchymal tissue is our stem cells or embryonic tissue for which all connective tissue arises. So mesenchymal tissue is that basic tissue that then it differentiates and turns to other types of cells to give me the final product. In this case, we're talking about bone. So we'll see two sheets, one here and one here, of mesenchymal tissue that'll gradually migrate and change with the blood supply to give me the actual structure of bone. How do we do that? Well, the mesenchymal cells turn into osteoblasts. Some books will say, well, you also see osteoprogenitor cells, which we'll talk about that in the next video. But it turns it into bone because the cells change. And because the cells change, their function changes. And what are they doing? They're secreting the matrix, which is that osteoid, to where you're getting the calcification. Calcification is creating the mineralization of the bone, specifically using calcium, calcium phosphate, calcium carbonate. So I look down below here, this dark purple is trying to show you the formation of bone, and you could start to see that it's looking more like spongy bone. So we're turning this into spongy bone. And then on the top, I have a membrane sheet of tissue, that mesenchymal tissue, and then also here on the bottom. So in between two membrane sheets, I'm creating this type of bone, and it occurs in dermal bones. Versus when we look at endochondral, this is showing you a long bone. So a lot of our long bones go through this process to where they're using now hyaline cartilage, to where we occur at the epiphyseal plate. So this section here, at the epiphysis and then the diaphysis, there's a section in between there, a region called the metaphysis, and this is where I have hyaline cartilage. This is matching on this side to where there's different zones on how it develops, but basically you're going to have hypertrophy or dying off of cartilage cells. And where do those cells come from? We start with mesenchymal, then it turns into hyaline cartilage, so we're using chondroblasts and chondrocytes to use this as stacking cells. So they call it an epiphyseal plate because it's literally like we're stacking plates of cartilage that will then be replaced by bone. We're taking one tissue, turning into another. That's an ossification. So once we're done growing, depending on the bone, like I said, this could take years, it turns into a epiphyseal line. So epiphyseal plate and line is at the point in development. A plate is when it's growing, a line is when it's finally done. So for example, some bones take a couple decades for them to actually finish their product. So what we see as a difference here is that hyaline cartilage model that we're using, and then it starts to turn into bone. So when I look at the dark purple over here for spongy bone, that's forming these dark little purple sections here. So it's very baby spongy bone that we're looking at. So intramembranous and endochondral ossifications is understanding how do we get to the final product of bone. We use our cells to create the matrix, but we can't do that without a foundation. We both start with mesenchymal tissue, and then it just depends on where we're at, which bone. Are we just using mesenchymal, turn that into osteoblasts, osteocytes, or are we using hyaline cartilage as a model? This is intramembranous and endochondral ossification. In the next couple of videos, we'll break down the two and just go the order of the steps of the cells and how they differentiate. This is intramembranous ossification, which is bone development. So we're discussing just this type. In a previous video, we briefly compared the difference between intramembranous and endochondral ossification. Remember, this is bone development, and we're taking one tissue and turning it into another. We see that throughout the course of our body in different parts, that things change and specialize. That's differentiation. Our body has the ability to change from one cell to the next for the purpose of creating some type of product. In this case, it's bone. When we talk about intramembranous ossification, it's in between membrane bones, dermal bones. We discussed that it's part of like the mandible, some of my bones of my cranium, my clavicle. These are dermal bones that I can feel right through my skin. How they develop is starting with mesenchymal tissue. So in the previous video, we looked at the same pictures, but it's good to highlight what's happening here, that this picture is describing this picture, and it's a point in time of the development. But essentially, we have mesenchymal tissue, which is our basic stem cells. So what is mesenchymal tissue? It's our stem cells, our basic embryonic tissue for which all connective tissue arises. In other words, mesenchymal tissue can turn into other types of tissue just besides bone or cartilage. You could turn into things like connective tissue proper, dense, and loose. So as we describe this, we're specifically looking how do we form our two types of osseous tissue. Remember, that's spongy and compact bone. So what are our two types of osseous tissue? Spongy and compact bone. But we got to get to that point. We got to be able to develop it, and then they got to grow. So how they develop is through intramembranous ossification when we talk about our dermal bones. So we start here with a sheet of mesenchymal tissue and a sheet of mesenchymal tissue. And we're bringing in blood supply. Remember, one of our functions of bone is blood formation, but it's also heavily used for the development of bone to bring in the supplies we need for it to develop. And that's why I think of bone development as bringing in the supplies and then it can grow. So we start with mesenchymal tissue and usually two sheets of it, to where the mesenchymal cells are migrating, but they start to change or differentiate into osteoblasts. Remember, you also have osteoprogenitor cells, which are then the stem cells of bone. So depending on the text, sometimes mesenchymal will turn into osteoprogenitor and then osteoblasts. You'll see some texts that'll say it'll go straight from mesenchymal and skip osteoprogenitor straight to osteoblasts, but you still have the presence of osteoprogenitor cells. Those are the stem cells for bone itself. So we go from mesenchymal to blasts. Remember, baby cells for the bead. Blasts are the ones secreting the matrix, because we know that majority of the bone is actually what the cells are secreting, which is the matrix. That includes our protein fibers, primarily collagen fibers, because we have three types. You remember those three types? Collagen, elastic, and reticular. Collagen is for our strength, so we use it for bone, and it's the most abundant fibers. So osteoblasts are secreting the matrix of collagen fibers, but then also includes that osteoid, that compound that creates the ground substance. And we start to mineralize the bone, and we do that through calcium. So calcification occurs as well to give us the mass, that hardened material, which is calcium phosphate, calcium carbonate, primarily. So that was a lot to say just what's going on with osteoblasts. But mesenchymal cells differentiate and turn into osteoblasts to actually secrete the matrix. Remember, this is occurring within now this purple area because this is the start development of bone, specifically spongy bone. So those osteoblasts will continue to secrete the matrix. Remember, as they get older, they turn into osteocytes, and they tend to form a little bubble around them called a lacunae. So osteoblasts turn into osteocytes to help maintain the tissue. Once I have these cells, I'm creating that product, and we call this spicules or trabeculae. Spicules is the basic little branch that starts, and as it all branches together like a tree, it becomes trabeculae. So if I just took little pieces of this in segments, like this is a spicule, that combines with a spicule. Here's another little strut here, a spicule, and it just starts forming all together, which is called trabeculae. So you might use those terms interchangeably in some texts. Spicules turn into trabeculae. Once I have that final branching, now I can start to form my two types of osseous tissue, spongy, and then it could continue to develop and turn into compact bone depending on where we're at in the bone and what type of bone it is. So it's just the basic steps, but the key is understanding that it's the change that we are replacing one type of tissue, mesenchymal tissue, and with our blood supply to bring in the actual cells that'll turn into the bone-making process of intramembranous ossification. So as soon as I see the difference between the two from intramembranous, I just see two sheets of tissue versus when we look at endochondral ossification is our next video, and that's seeing hyaline cartilage. So when we compare the two slides, I'm really just looking for the bubbling of cartilage cells that we'll look at in the next video. This is intramembranous ossification. This is endochondral ossification. Endochondral is referring within cartilage. We looked at intramembranous ossification in a previous video to where it's within membranes of mesenchymal tissue. And in endochondral, we still use mesenchymal tissue. We just add an extra step of using hyaline cartilage. This is often confusing for students because it's like, what the heck are we talking about here? This is about how we develop bone, because remember we said once we get into connective tissue, we see a lot more in the spaces, the interstitial spaces of cells, of what the cells are making. And this is the matrix. So as we develop bone, we're taking one tissue and turning it into another. That's an ossification. In this case, we're using cartilage, hyaline cartilage. So what this slide is trying to show you is that when we look at long bones, we tend to see more hyaline cartilage. And the point here where this arrow is, and I magnified it on this side, this is our epiphyseal plate. And there's different zones on how we categorize the development of it. I'm just going to focus on where we have this hypertrophy, or the building in larger cells of hyaline cartilage cells, specifically chondrocytes, that start to bubble up. And then we're going to replace them with osteoblasts and osteocytes, because they're the ones that make the matrix. So remember, as we refer to a long bone, we're going in this development here to where we build or develop first in the diaphysis, which is the shaft, and we'll call that the primary ossification center. And as we gradually build out, we're building into the epiphysis or epiphyses, which is the secondary ossification center. And where we stack then that cartilage is in the epiphyseal plate. So epiphyseal plate is that point of development. As it fully develops, sometimes up to 20, 25 years, then it becomes an epiphyseal line and forms bone. So as we describe this, and we just started with the basics of cartilage in the embryonic development of bones within our first 6 weeks inside the womb as a fetus, we're all cartilage, and we're gradually changing into bone where it's needed because the cells become specialized. They differentiate. In this case, when we look at a long bone, we see a lot of cartilage, and we're starting in this developmental process in the middle, which is the primary ossification center. And what we're doing is mineralizing the bone at the same time. And how do we do that? We do it with calcium phosphate, calcium carbonate. That's the mineralization or calcification of bone. So what this is saying is we're going to bring in the materials to help the bone grow. So it mentions perichondrium up here. This is referring to the outside layer of the bone, which is cartilage to start. Later, it becomes the periosteum, which is referring to now that it's bone towards the outside. So now we go from perichondrium to periosteum. We're building in this primary ossification center, and it gradually then going to bring in blood supply to start to build in our secondary ossification center, which is in the epiphysis. So what's happening here is we start with our basic embryonic cells, our stem cells, which are mesenchymal cells. They will turn into the cells that help to make bone. You'll see osteoprogenitor cells, which are stem cells for bone specifically. They turn into osteoblasts. And osteoblasts are the ones that are starting to secrete the matrix. And when we see that, that's coming through the blood supply to take over that cartilage that we built. So this is where we start to see that epiphyseal plate that's building as a long bone. And when that epiphyseal plate continues to grow, we just stack cartilage cells. And the specific cartilage cells are my chondrocytes. And those chondrocytes, we go through what's called hypertrophy or hypertrophy. They get larger and larger and die off, and we replace them with the bone cells. So what you're seeing here is from this growth plate, all this dark purple here is starting the formation of basically baby bone. And you can see it looks somewhat porous. It's forming spongy bone, and then it'll gradually turn into compact bone where needed. So we go through mesenchymal cells. They turn into cartilage, so chondroblasts, chondrocytes, because those are the cells that make my hyaline cartilage. We take over that hyaline cartilage model, so we built the framework for the bone, but then we replace it with osteoblasts and osteocytes to secrete the bony matrix. There's two types of tissue that we're trying to develop, spongy bone and compact bone. So that's the big difference with endochondral. We see it in long bones, and we're using a hyaline cartilage model. When I look at an intramembranous slide, I don't see this stacking in the bulgy chondrocytes. So when you're looking at histology, just process elimination, I'm trying to find that cartilage model first. If I don't see it, then I know I'm looking at intramembranous. This is endochondral ossification, the development of bones specifically for long bones. We're going to cover some of our cranial bones, and then we'll look at the sutures associated with cranial bones, and then move on to facial bones. So when we look at our cranial bones, there's 8 bones total, but only 6 terms because 2 of the bones have 2 of them. So as we cover the frontal bone, we start with just the frontal side. So our forehead is our frontal bone. That's number 1. Over the top, we have 2 parietal bones. As they go posterior, occipital bone. I tried to outline it here for you. This is occipital bone. And then on the sides, I have a temporal bone where my ear is, temporal bone. And then same thing on the other side, temporal bone. When I look inside the skull, we're going to look at ethmoid and sphenoid. And I'm going to turn it this way. This is the anterior. Tried to highlight this as best I could, but the green here, this is the part of the ethmoid bone, one of our pneumatized bones. And then where I drew the purple that's creating the boundary there, this is the sphenoid bone. So 8 bones total when we look at our cranial bone. 1 frontal, parietal, 2 and 3, occipital on the back, 4, my temporal, 5 and 6. And when I open it up and look inside our cranial fossas at the floor here, ethmoid 7, sphenoid 8. So our 8 cranial bones. Let's look at some of the sutural bones. This is dense fibrous connective tissue to connect our bones together. So these sutures that come across, first we'll start with, as it creates this boundary to connect my frontal and my parietals, this is the coronal suture. So coronal suture. Just like we cover sections or planes, a sagittal cut, this is the sagittal suture. So we did coronal, sagittal. As they come to the posterior side with the occipital bone, this outline here, this is all lambdoid or lambdoidal suture. And then on the sides where I see my temporal bone, this is squamous or squamosal suture. So squamous suture. So as we cover the sutures, they're combining to the bones. Now that we've talked about the cranial bones, let's look at some of the bony landmarks or bony markings of those bones. So when we look at our frontal bone, inside is the frontal sinus. So I need a sagittal cut to see that. As I come across and look at the posterior side, and we go back to our occipital bone, some of our bony markings, if I look at this bulge here, this little projection is called the external occipital protuberance, and we'll attach a ligament there that's called the nuchal ligament associated with liplash. So this is the external occipital protuberance. Coming off of it on either side is this line, superior nuchal line. External occipital protuberance, superior nuchal line. Then below, there's an inferior nuchal line. that's underneath or inferior to my superior. And then as I run down, this is my occipital crest, occipital median crest, occipital median crest. This will lead down to this big hole that we call the foramen magnus. Foramens are holes. It's a larger hole, magnus, so foramen magnum. So the hole there for our brainstem is foramen magnum. On either side, I have a smooth projection here on either side of foramen magnum. This is called occipital condyles. Occipital condyles is the attachment for the C1 vertebrae, which is called my atlas. You say, yes, I love learning this stuff. So occipital condyles. When we look at our temporal bone, when we look at right or left, I'm using this projection here, which is a process, and this is called the zygomatic process. And to me, it's almost like you're using it as like a Bluetooth microphone. That's how I can tell right or left with this. But this is all temporal bone. That projection coming off is zygomatic process because it leads to my zygomatic bone. When I look at other projections, I have two more processes that we'll learn. This big one is a mass. This is called the mastoid process. Mastoid process. And then just like a stylus you have for an iPad or some of our phones, this projection that comes underneath, if you can see it there, that looks like a stylus or a pen, styloid process. So styloid process, mastoid process, where I can pick my ear and I put my hole in the ear where the sound travels in. So when I hear things, this is external acoustic meatus, also called external auditory canal. External acoustic meatus or external auditory canal. When I open it up and I look inside, I have these big bulges here. And so all of this is called the petrous part or petrous portion. This petrous part is where I hold all my inner ear structures for hearing, my cochlea, and balance and equilibrium. So all my inner ear structures are housed inside here to protect it. This is called the petrous part, another bony marking of the temporal bone. When I look at the ethmoid bone, part of it I can see sticking out on the anterior cranial fossa here, this space. The other part of it is inside the nasal cavity. So this bone sits right in here. When I look at this whole middle plate here, that's called the nasal septum. It's a general term to describe two bones coming together, but the top half of this is called the perpendicular plate. The perpendicular plate is one of our bony markings of the ethmoid bone. So the top half is perpendicular plate. It'll come up and combine with some of our structures here that's still part of the ethmoid bone. So as I turn it this way, there's a projection here that kind of looks like a shark's fin. And this is called the cristagalli. The cristagalli. That projection that sticks up, cristagalli. The cristagalli sits on what we call a cribiform plate. A cribiform plate. The cristagalli sits on the cribiform plate. So this is really small because this is all just the ethmoid bone just in this area. Where that cristagalli sits is on either side where I have the cribiform plate. And what's unique about it is I'll have, if the pipe cleaner was my nerve, my olfactory nerves for smell sit on either side of this. I'll also use the cristagalli for some of our meninges attachments for dura mater. But when I look at my cribiform plate, it has holes in it. And those holes are called olfactory foramina. Foramens are holes, plural is foramina, olfactory foramina. So when I breathe and I smell the molecules of whatever I'm breathing in, it's going to go through the nasal cavity, through those olfactory foramina, and stimulate the olfactory nerve. So I have cristagalli, which means crest of the rooster, and then cribiform plate is what it sits on either side, and then the holes within the cribiform plate are olfactory foramina. Now I look at the sphenoid bone, which I said was part of the floor of the middle cranial fossa. When I look at the sphenoid bone, I can see that it has what's called lesser wings and greater wings. The lesser wings are at the anterior side here. So lesser wings at the top. And when you look at the bone disarticulated, it looks like the antlers of a bat. So this is lesser wings. The rest of this is greater wings. So greater wings and then the small lesser wings. What's going through the lesser wings is the optic canal. As I put my pipe cleaner through the holes of the lesser wing, so I have the pipe cleaner going through the holes of the lesser wing, and that lesser wing has that hole for one specific reason. It's called the optic canal. So the optic canal is for the eyeball. So I'm using the optic nerve, pretend my pink pipe cleaner is my optic nerve, to connect to my eyeball. So going through the lesser wing, there's a hole called the optic canal. And so as you're studying this, write that in your notes, that it's the hole in the lesser wing. In between my two wings, lesser and greater, I have what's called the superior orbital fissure. So in between my wings, I have a gap, and that's called a fissure. Superior orbital fissure. And so when I show it this way, it's another for blood vessels and nerves. But this attachment, and I'm going to pull out the optic nerve, so then you can see that space in between is superior orbital fissure. So two holes there right at the lesser wings and the greater wings. And then I have this cradle here. We call this the sella turcica, which means Turkish saddle. And it's curved like a C. And what it's supposed to do is I'm going to use this slime, and I'm just going to put it inside here to show you how I can seat the pituitary gland. So one of our glands, pituitary gland, sits in the sella turcica. So that space, as I take this out, is sella turcica. And it's literally like a bed or a crib or a cradle to hold my pituitary gland. Okay. And then we're going to learn three holes coming off the greater wing. So three holes in the greater wing are called foramen rotundum, foramen ovale, and foramen spinosum. When I look here, three holes. This first hole is called foramen rotundum. And this will repeat on both sides in the greater wing, but foramen rotundum. And then I have foramen ovale. And then right below it, I have foramen spinosum. So there's three holes that run on the sides through the greater wings. And we always have these holes for something. It's either blood supply, nerve supply, or both. So foramen rotundum, foramen ovale, and foramen spinosum. And I covered that a little bit with the purple, but that is spinosum. So if you can see three holes there, just remember ROS, rotundum, ovale, spinosum. So three holes that we look at. The other thing is when I go through the feet of the sphenoid bone, it's like kind of like looking at the bat. Underneath, it sticks out on either side. This is called the pterygoid process. Pterygoid process, and it's just these little sections of the bone. And when I show you this picture, you can kind of see how it sits inside the cranium, but those projections that come underneath, pterygoid process with the silent P. And now we're covering facial bones. So all of our facial bones, and then we'll look at some of the actual landmarks associated with those bony landmarks within the bones. And then also we'll look at the eye socket. The eye socket's actually 7 bones, and our next video will describe those 7 bones that make up the bony orbit or the orbital complex. So when we look at our facial bones, part of it makes up the eye socket. And what we'll look at is we already covered frontal bone. Then we move on to nasal bones. So the bridge of my nose is nasal bone. The rest of it is mostly cartilage. This is my nasal bone. In between the two nasal bones is where I have a suture called the intranasal suture. And then coming up, that runs across This is frontonasal suture. Frontonasal suture because it's connecting nasal bones to the frontal. And then very light, but just that little squiggly line there, this is frontal suture, also called metopic suture. So this is frontal suture running across like it's an upside down T. Frontonasal suture, and then internasal suture in between my nasal bones. So I have my nasal bones. When I come inside the eye, just this little small area here is the lacrimal bone. And it's where your tears come out when you're crying, when you gotta learn all this stuff. This is called the lacrimal bone. And lacrimal bone will help as we produce tears here, and it rolls across my eyes. It'll fill up in a duct here that we'll talk about later. But where that occurs, it's so small, the bony landmark is pretty much all of the bone, and it's called the lacrimal sulcus or the lacrimal groove. So this is my lacrimal bone, but the landmark is the lacrimal groove. So when we talk about identifying things, is it the bone versus the bony marking? It depends on how it's asked. So the landmark is the lacrimal sulcus. When I come down and we'll look at my cheek, this is zygomatic bone. Zygomatic. And zygomatic bone has a process here that's called the temporal process. And the temporal process connects to the temporal bone. But it's connecting by way of the zygomatic process of the temporal bone. That should be confusing the first time I say it. The two bones come together. Zygomatic bone and temporal bone. Those create what we call the zygomatic arch, which is that nice curve of the cheek. What we're describing are the two bony landmarks that are coming together. So the process is the opposite of the bone. So if this is zygomatic bone, and I divide all of this in just half, this anterior portion is called the temporal process. The other side is the zygomatic process that's part of the temporal bone. So zygomatic bone, temporal bone. The processes are the opposite. Zygomatic process, temporal process. As I come down then, where I grow a mustache and it'll come up along the sides of the nasal bone, this is all maxillae or maxillary bone. Maxillary or maxillary bone. And then I also have the vomer bone. The vomer. Previously we talked about the nasal septum, which is that whole middle sheath. That whole middle sheath is the nasal septum, but the top half of this sheath is the perpendicular plate of the ethmoid bone. The bottom half is the vomer. Those two come together to become the nasal septum. If they break or they don't fuse together straight, it's called a deviated septum. The other thing we can see inside, which is its own separate bone, is the inferior nasal conchae. So on either side, this fold just on the bottom here and here is inferior nasal conchae. And so we also have middle and superior that are part of the ethmoid bone. On the picture that I'll show in the video, you can see that a little bit better. But as I describe all these folds inside, they're called conchae. So it's everything besides the nasal septum. As I breathe, it creates a turbulence to help clean, warm, and humidify the air in preparation for respiration. So I look inside, the bottom folds on either side, inferior nasal conchae. The bone that comes down here to project is the vomer. And we were leading to then the mustache bone is the maxillary bone, which also includes the roof of the mouth on the anterior side. So this is anterior. The roof of the mouth, this is all still the maxillary bone, but the bony marking is called the palatine process. The palatine process. As I go to the posterior, then we see the palatine bone. So I highlighted that with green there, palatine bone. So this can be confusing because the anterior portion is the maxillary bone. The posterior bone is the palatine bone. But the actual name of the landmark or bony marking is the palatine process. So I have two bones that really are creating that roof of the mouth. When I look at the teeth, and we see where the teeth are coming together, but I have these projections, and not the teeth itself, but these are called alveolar processes or alveolar parts. So we'll often see alveolar parts as just referring to these little projections that help create that socket for the teeth to go into. We'll see it part of the maxillary bone, but then when we see it on the mandible. So let's get into the mandible. As I look at my jaw or my mandible, it's really just a nice L. And it just repeats on both sides. So when I describe the L, the mandibular ramus is the first part of the L, and then the body is continuing on with the letter L. So mandibular ramus, mandibular body. When I look at the projections that are up at the top here, the one that connects into the temporal bone, it's connecting into the mandibular fossa of the temporal bone. You can see a little bit of cartilage there. It's actually fibrocartilage for that shock compression, but it's going to sit inside of there. What I'm describing is the condylar process. So this is the condylar process that's going to go into the mandibular fossa. On the anterior side, it's called the coronoid process. So two processes, condylar process, coronoid process. But it's the condylar process that goes into the temporal bone at that mandibular fossa. As I come down, we see this mental protuberance. This is referring just how the jaw comes out here, mental protuberance. And then I have two holes here, which are called mental foramens. Remember, holes are foramens, and I actually use that for, remember, holes are not just holes. We put something in there that's extensions of nerves, so I can feel that. So these holes in front are mental foramen. We're covering the bony orbit, or the orbital complex, or the eye socket. We've talked about some of our different cranial bones and facial bones. This is just a conceptual idea that the 7 bones that make up the bony orbit fuse together to give me what holds my eye. So we're describing just those, and I tried to color this the best I can, but this red circle, as I pull it into this black circle, we're describing those bones that come together. So there's 7 bones: frontal, zygomatic, maxillary, sphenoid, palatine, ethmoid, and lacrimal. Those fuse together to give me what's called my bony orbit. So frontal bone, which is my forehead, contributes down to my cheekbone, my zygomatic bone. We learned sphenoid bone that makes up part of my middle cranial fossa, the floor inside when I open up the skull. And then also the same with ethmoid as we get towards the anterior cranial fossa. Remember, ethmoid has that perpendicular plate, and part of that will come down and stick out here with my nasal conchae. My lacrimal bone is where my tears develop, so just on the corner of my eye here. So I get lacrimal bone, ethmoid bone, and palatine bone. And then down to my maxillary bone, which is my mustache bone and part of the roof of my mouth, but it still comes up all the way around my nose. So we'll often use a mnemonic for these. You'll see different ones out there. I prefer you just learn the bones, but one I see students use is called Please Feed My Zebra, but please is spelled incorrectly. It's spelled as P-L-E-S. So the P-L-E-S means palatine, lacrimal, ethmoid, and sphenoid. And then so I said please feed, just the F is my frontal, my, the M is maxillary, and zebra, Z is the zygomatic. Sometimes not a fan of mnemonics, as we've seen in a previous video, because now you're learning something completely different that's not associated with the eye at all, but some students like using them. So please feed my zebra, but please is spelled P-L-E-S. This is how you can remember the 7 bones, but you're already learning them independently. So this is just a concept of understanding the bony orbit or the orbital complex is how these 7 bones fuse together to give me one distinct area to hold my eye. We're covering the vertebrae, and we'll start by comparing the differences between cervical, thoracic, and lumbar, just so we can tell the differences between them, because in most exams or tests, they ask them separately. So let's look at this as we describe the 3. We put them together, we can tell by size. This is a cervical vertebrae, this is a thoracic vertebrae, and this is a lumbar vertebrae. Now, just doing cross elimination, the best way I can determine that I have a cervical is when I look inside, there's actually 3 holes that make up a cervical vertebrae. And what's unique to them are these holes that are in my transverse process, and these are called transverse foramina. Transverse foramina. These are unique to cervical vertebrae that I don't see in my thoracic or my lumbar. So just by process elimination, I could already determine is it cervical or not. And some of the cervical vertebrae, not all of them, but on their spinous process, you can see these 2 little projections. That's called a bifid spinous process, that there's 2 heads coming off of it. Versus when I look at the other 2 types, thoracic and lumbar, they don't have those spinous processes that project 2 different pieces. So I can already rule out a cervical once I look at those 2 holes, again, which are transverse foramina. When I compare thoracic versus lumbar, the easiest way for me is when I look at the hole in the center, which is called the vertebral foramen. Remember, foramens are holes. So that hole in the middle on the left, this one's a thoracic, and it's a nice circle. When I look at a lumbar, it's a triangle. So I can compare the 2 just by that hole. The other thing I just look at is the design of it. When I look at the centrum or the body, it appears to have a heart shape for the body. Versus cervical and lumbar, I don't see that same heart shape. The other thing I just look at is just a general description of it. A lot of my students will say a thoracic looks like a giraffe or an elephant, as if this was the elephant's trunk, which is the spinous process, versus a lumbar tends to look like a moose. So I just go by these blunt processes and the appearance of it, that a lumbar tends to look like a moose. Now, as I get into the different structures, one thing to notice when we identify our processes, that the spinous process is our further posterior structure, bony landmark, that this spinous process is always going to point down. This spinous process is always going to point down. And so when we look at our spinous processes, these are the further posterior bony landmarks of each vertebrae. When I look at the sides, as if it's like the wings, these are transverse processes. So transverse processes, transverse process, transverse process, transverse process, and a transverse process. When I look at a cervical, I know I have a transverse process, and that's because it has holes inside. Remember, those are called transverse foramina, which are unique to a cervical vertebrae. Now, when I looked to how we create the actual vertebral arch and the circle around it. So as I go around and create this, all these bony landmarks, what we're describing first is all of them have this, but as I look at the centrum or the body, I describe these as like bridges. So in order to get from the body or centrum to the transverse process, I go through just this little bridge called a pedicle. And this is very small and difficult for students at first, but I just imagine as if I'm to drive from here to here, my body to my transverse process, I drive along this pedicle. In order to get from transverse process to what I'm holding is the spinous process, this bridge is called the lamina or laminae. So as I go from body to transverse process, I have this little connection called a pedicle. In order to get from transverse process to spinous process, I go through the laminae. So I'm describing those bridges. Now, how do I connect the vertebrae? What we use are called articular facets. And what I'm showing here is I'm going to take a couple thoracic and put them together. And where they're connecting are on these flat sections of the bone. And so where I'm sliding, these are called articular facets. And so when I look at it, to me, I describe it as if I'm holding my hand up with my arm. The flat, smooth side of this is called the superior articular facets. So it's like the ears of the elephant. So superior articular facets. And it's that smooth hand that's being held up by the arm. The arm behind it is the process. Superior articular process holds up the flat hand, superior articular facet. So I'm using the superiors to attach to the inferior. So as I flip it, these superior articular facets now appear flat on this side because this is the inferior articular facet. And what holds it up is the arm, the inferior articular process. So I'm using my processes and my facets to come together. And they come together at those facets. So on top, I'm using inferior articular facets to connect to my superior articular facets. The other unique thing about a thoracic vertebrae, as I describe these, is we're connecting ribs. So on my ribs, I'm going to use my vertebral end of my ribs to connect to these little projections here, here, and here. This is superior costal faucet. This is inferior costal faucet. And then on the transverse process, that divot is transverse costal facet. So I can flip it on the other side too. The depression on the transverse process, transverse costal faucet, inferior costal faucet, and superior costal faucet. Those are only unique to a thoracic vertebrae, versus all the other bones have those other structures or bony markings that we learn. So transverse process, spinous process, superior articular facet. Behind it is the superior articular process, vertebral foramen, and body. So we can describe all the same for all three. When we look at how we describe our cervical vertebrae, what's unique to them is the first two and number 7. So now I'm going to show you 1, 2, and then we're going to get all the way down to 7, C7, because I have 7 cervical vertebrae, 12 thoracic, and 5 lumbar. This flattest one here, these are all cervical vertebrae, and how do I know that? This flat one still has transverse foramina, but it also has the widest vertebral foramen out of all of them. And that's because it's C1, also known as the atlas. And this is the vertebrae that helps us to say yes. And so I'm using these articular facets to actually connect to the occipital condyles of the occipital bone. So I have atlas, which is my flattest bone, and we look at it, it's got those wide features to it, but it's flat, versus number 2, our C2 cervical vertebrae, is called the axis. So atlas and axis. Now remember, T becomes before X, so atlas helps me to say yes. Axis helps me to say no. Now what do I mean by that? Is that when I put the vertebrae on, we're going to use it to swivel, to be able to say no, I don't want to learn this stuff, or yes, I do enjoy learning this stuff. How do I know this is axis? A lot of students will say it looks like Buddha, and this is Buddha's head. And Buddha's head is called the dens, also known as the odontoid process. So dens or odontoid process. And this is how I identify what's unique for all of our cervical vertebrae as C2, the axis. And then lastly, we said our last vertebrae for cervical is C7. What's unique about C7, it starts to transform almost looking like thoracic, where I have that long, slender spinous process. But this spinous process is unique because we're going to attach a ligament here. We call this the vertebrae prominence. And this is going to attach one of our ligaments that goes to our occipital bone. So when we experience whiplash, it's impacting the cervical vertebrae. But we have more attachment points because we have a lot more movement in our cervical vertebrae. So that's a description of how we understand our different vertebrae. And then as we come down from lumbar, we're going to get to the sacrum. So our last vertebrae, our number 5 lumbar, is going to attach to my sacrum. And then after that, I'll attach the coccyx. So when we look at this, now we're describing how we have multiple landmarks for the sacrum and then the coccyx. So the sacrum is 5 bones that have fused together versus the coccyx or coccygeal bone can be 3 to 5. And typically we teach it as 4, but it varies on the person. In this case, we're seeing 4 bones. When we look at the sacrum, we're going to use this to attach as part of our pelvic girdle to the coxal bone. So as we describe it, I'll show you it still has that weight-bearing part of the centrum of the body. As they come down, we actually end up having some of our spinal nerve endings coming through what's called the sacral canal, and it'll go all the way down, and there's a hole here called the sacral hiatus. Because the spinal cord ends around lumbar 1, lumbar 2 vertebrae, and then it starts to expand in what we call the cauda equina, which means horse's tail. So when you look at a picture of it, you'll have all these nerve endings that are going down here to stay protected in a sacral canal, but then you'll end up with still a hole that ends up here called the sacral hiatus. Along the sides, you'll see more holes, and these are called sacral foramina. Remember, foramina are whole, plural is foramina, sacral foramina. And then down the middle, you'll see the median sacral crest, median sacral crest. And this is trying to show you all the spinous processes of those 5 bones that have fused together. So median sacral crest, our foramina, sacral foramina. And then on the sides, I have auricular surface. On the lateral sides, auricular surface. Auricular surface. And this is to attach the sacrum. So we have sacrum and coccyx. We're covering the bones of the hands and the feet. We're starting with a right hand, and we're looking at the palmar view or anterior view in the anatomical position. And we're learning the carpals, the metacarpals, and the phalanges. We'll start with our carpals, and in our wrist we have 8 bones. The way I teach this is with a mnemonic to start lateral and count 4 bones over to the medial side, and then go back to the lateral side with 4. We use the mnemonic so long to pinky. Here comes the thumb. So as we learn this, the first one that's the most proximal is scaphoid, and it's kind of shaped like an S. So I remember the S in scaphoid. Scaphoid, lunate, triquetrum, and we can see triquetrum when we turn it. This is triquetrum, and on top is pisiform. So long to pinky, and now I continue back with the next 4. Here comes the thumb. Hamate, capitate, trapezoid, and trapezium. Hamate, capitate, trapezoid, trapezium. Students tend to get these 2 last ones confused. I just remember that the D becomes before M in trapezoid and trapezium. Scaphoid, lunate, triquetrum, pisiform is the rock on top, hamate, capitate, trapezoid, trapezium. Now to our metacarpals. 1, 2, 3, and 4, and 5 metacarpals. Now we add the number. Number 1 metacarpal, number 2, number 3, number 4, number 5. These are all my metacarpals. I just remember the big guys, number 1, the thumb, and the big toe are number 1. So metacarpals to my digits or phalanges. For the finger, we call it the pollex. It's got 2 bones to it. It's got a proximal phalange and a distal phalange, so 2 bones. The rest of my phalanges have a proximal, middle, distal. Proximal, middle, distal. Proximal, middle, distal. Now we can name them with the number 1, 2, 3, 4, and 5, plus its designation of proximal, middle, distal, and that it's a phalange. So this would be number 3, proximal phalange. This would be number 4, middle phalange. This would be number 5, distal phalange. This is my hand. When we look at the foot, this is a right foot. And we'll start with our 7 tarsals, then the metatarsals, and then back to phalanges. There's 7 tarsals. Some students like to learn it with the mnemonic. I like to just learn the terms in this case because I think they're bigger bones, easier to learn as you study them. The big one, which is the heel, is the calcaneus. So it's the heel what I step back on, dorsiflexion, and I have the calcaneus. On top, T for top, this is all the talus. And it curves here, and it looks like more than one bone. From here to here, this is all the talus. Calcaneus and talus. Running across is navicular. Calcaneus, talus, navicular. And then I have 1, 2, and 3 cuneiforms. I have a medial cuneiform, intermediate cuneiform, and a lateral cuneiform. And then lastly, on the lateral side, the one that's supposed to look like a cube, this is cuboid. So 7 tarsals: calcaneus, talus, running across, navicular, 1, 2, and 3 cuneiforms, medial, intermediate, and lateral cuneiforms, cuboid. Similar to the hand, now we count our metatarsals, except we go the opposite direction. Remember we said thumb and big toe are number 1. So this would be 1 metatarsal, 2, 3, 4, and 5 metatarsals. My phalanges, for the toe, we call the thumb the pollex. For the toe, we call it the hallux. 2 bones, just like the thumb. It's got a proximal and distal phalange. For my toes, 1, 2, and 3. Proximal, middle, distal. Proximal, middle, distal. Proximal, middle, distal. Proximal, middle, and distal. Counting the numbers, this would be number 2, proximal phalange. This would be number 3, middle phalange. This would be number 4, distal phalange. This is my foot. We're covering the bones of the hands and the feet. We're starting with a right hand, and we're looking at the palmar view or anterior view in the anatomical position. And we're learning the carpals, the metacarpals, and the phalanges. We'll start with our carpals, and in our wrist we have 8 bones. The way I teach this is with a mnemonic to start lateral and count 4 bones over to the medial side, and then go back to the lateral side with 4. We use the mnemonic so long to pinky. Here comes the thumb. So as we learn this, the first one that's the most proximal is scaphoid, and it's kind of shaped like an S. So I remember the S in scaphoid. Scaphoid, lunate, triquetrum, and we can see triquetrum when we turn it. This is triquetrum, and on top is pisiform. So long to pinky, and now I continue back with the next 4. Here comes the thumb. Hamate, capitate, trapezoid, and trapezium. Hamate, capitate, trapezoid, trapezium. Students tend to get these 2 last ones confused. I just remember that the D becomes before M in trapezoid and trapezium. Scaphoid, lunate, triquetrum, pisiform is the rock on top, hamate, capitate, trapezoid, trapezium. Now to our metacarpals. 1, 2, 3, and 4, and 5 metacarpals. Now we add the number. Number 1 metacarpal, number 2, number 3, number 4, number 5. These are all my metacarpals. I just remember the big guys, number 1, the thumb, and the big toe are number 1. So metacarpals. To my digits or phalanges. For the finger, we call it the pollex. It's got 2 bones to it. It's got a proximal phalange and a distal phalange. So 2 bones. The rest of my phalanges have a proximal, middle, distal. Proximal, middle, distal. Proximal, middle, distal. Now we can name them with the number 1, 2, 3, 4, and 5, plus its designation of proximal, middle, distal, and that it's a phalange. So this would be number 3, proximal phalange. This would be number 4, middle phalange. This would be number 5, distal phalange. This is my hand. When we look at the foot, this is a right foot, and we'll start with our 7 tarsals, then the metatarsals, and then back to phalanges. There's 7 tarsals. Some students like to learn it with a mnemonic. I like to just learn the terms in this case because I think they're bigger bones, easier to learn as you study them. The big one, which is the heel, is the calcaneus. So it's the heel what I step back on, dorsiflexion, and I have the calcaneus. On top, T for top, this is all the talus. And it curves here, and it looks like more than one bone. From here to here, this is all the talus. Calcaneus and talus. Running across is navicular. Calcaneus, talus, navicular. And then I have 1, 2, and 3 cuneiforms. I have a medial cuneiform, intermediate cuneiform, and a lateral cuneiform. And then lastly, on the lateral side, the one that's supposed to look like a cube, this is cuboid. So 7 tarsals: calcaneus, talus, running across, navicular, 1, 2, and 3 cuneiforms, medial, intermediate, and lateral cuneiforms, cuboid. Similar to the hand, now we count our metatarsals, except we go the opposite direction. Remember we said thumb and big toe are number 1. So this would be 1 metatarsal, 2, 3, 4, and 5 metatarsals. My phalanges, for the toe, we call the thumb the pollex. For the toe, we call it the hallux. 2 bones, just like the thumb. It's got a proximal and distal phalange. For my toes, 1, 2, and 3. Proximal, middle, distal. Proximal, middle, distal. Proximal, middle, distal. Proximal, middle, and distal. Counting the numbers, this would be number 2, proximal phalange. This would be number 3, middle phalange. This would be number 4, distal phalange. This is my foot. We're covering the skeletal system. I'm going to mix the axillary and the appendicular system. We're going to start out with the sternum, and then we're going to work our way all the way down to the arm. One of our previous videos, we looked at hands and feet, so let's just start with the sternum. We can divide it into 3 sections. From my pointer up, this is all the manubrium. And then the bottom or distal portion is called the xiphoid process. Xiphoid means sword. Manubrium means handle. So the handle is the manubrium. Everything in between the manubrium and the xiphoid process is the body. So I have 3 regions: manubrium, body, xiphoid process. A couple other landmarks or bony landmarks to learn. On the top, this ridge here on top is called the jugular notch. So jugular notch. On the sides for the clavicle, clavicular notches. So clavicular notch, jugular notch. And then where the cartilage is connecting for the ribs, these are all costal notches. Costal referring to the ribs. So costal notches. Keep in mind, this is not bone. This is cartilage. What type of cartilage is this? Remember, there's 3 types of cartilage: hyaline, fibrous, and elastic. This is hyaline cartilage. So this is the sternum. As we move on to a rib and connecting the rib, I have 2 ends that we're learning. The smoother end is referring to the sternal end because we're going to get that connection to the cartilage of the sternum. So sternal end is my smooth end. My rougher end where I have these projections is the vertebral end. So 2 ends, vertebral end and sternal end. couple of the landmarks that we'll learn. The actual end or the head of the vertebral end is the head, and then in between is the neck. So at the vertebral end, I have head and neck, and then I have a tubercle. So I have this tubercle here. As I come down and I look on the inferior side, and when I'm going in the posterior portion of the bone, this is costal groove or sulcus. Maybe hard to see on the screen, but when you rub your finger through here, you can see a groove, and that's to protect some of our nerves and blood supply. And then when I determine right or left on this, remember I said that this is the sternal end, so it's got to go to the sternum either here or here, but I need that costal groove to be on the inferior side, but also posterior. So this stays down. This has to go to my vertebral end. So this is a right rib, if you can imagine it on my body. So a right rib. As we move on to the clavicle, this is our collarbone, but now we call it the clavicle. And when we look at this, the top part of it, or superior part, is smooth relative to the inferior portion. As we learn the inferior portion, that's where we identify a couple of our bony markings. Again, two ends. I have what's coming to the sternum. This is the sternal end, and this is the acromion end. The acromial end looks like a spoon to me, and it'll look like that on the scapula too. So as I come down to the sternal end, this is going to connect to the sternum either like this or like this. And so sternal end, acromial end, so two ends. And when I turn it on the inferior side, at the acromial end, we're learning this projection here, which is the conoid tubercle. Conoid tubercle. So it's a little bulge or bump on the inferior side. When I come over to the sternal end, there's a rough projection here called the costal tuberosity. So these can be difficult for students, but as I look at the smooth side is my top or superior, the bottom is my inferior. On the acromial end, we are learning the conoid tubercle, and the costal tuberosity is this rough projection as we get close to the sternal end. Right or left with this, I use again that the top is my superior side, that's that smooth section. And when I follow the acromial end, it curves like a spoon, and I want that spoon to project out anterior away from me. This is a right clavicle because I have to put this at the sternal end no matter what I do with this. But as I follow the acromial end, it comes out and points away. So this is a right. If I turn this way, the acromial end is going to stab me with that spoon. I don't want that. So this is a right clavicle. As we move on to the scapula or shoulder blade, it's kind of a triangle. So three sides of a triangle. So we name those as borders. This is a superior border. This is an axillary or lateral border because it's going to be at my armpit. And I know this is lateral because I have this connection here for my humerus, and that landmark is called the glenoid cavity. So that has to project lateral, and so that glenoid cavity is going to project this way. So I know this is my lateral side or lateral border, also known as axillary because it's my armpit. This is medial border because it's going to be more medial, and it's also called the vertebral border because it's closer to the vertebral column. On top, superior border. So three sides of the triangle. Lateral border, superior border, and medial border. As I look at these projections, these are processes, and the big one on the posterior side, this end is called the acromion or acromion process, and it's connected to the scapular spine, and this is what you can feel on your posterior side of your back. So scapular spine runs and becomes the acromion process. Scapular spine, acromion or acromion process. If you notice, it looks similar to the acromion of the clavicle. So they look similar. So I still have that spoon appearance. Acromion process, as I turn it and I go back to anterior, coracoid process. Coracoid process. So with the C and a C. Coracoid, acromion process. And then when I look with this scapular spine, I have a space above it called the supraspinous fossa. Below it, infraspinous fossa. So above the spine, supraspinous fossa. Fossas are depressions. Infra, below it. So we're learning those two spaces. When I go on the anterior side, and if to go anterior, I have to go deep. So we go sub or below. This space where I can rub my hand is called the subscapularis fossa. So subscapularis fossa, supraspinous fossa, infraspinous fossa. Why are we learning this? We're building the language. We're going to attach muscles here when we cover muscular system. When we look at that connection again, we said that space is called the glenoid cavity. There's two projections at 12 o'clock and 6 o'clock. One's called the supraglenoid tubercle at the top. At the bottom, infraglenoid tubercle. So 12 and 6 o'clock, supraglenoid tubercle, infraglenoid tubercle. How do I do right or left with this? Remember I said I need that connection for the humerus. So this has to point out either this way, or I have to turn it. It's going to go like that. But this is not going to sit well. When you feel this on your back, that subscapular area is going to be deep on my back. But the scapular spine has to point out posterior, and I need that connection for the glenoid cavity. So this is a right scapula. Moving on to the humerus, the first thing I want to show you is these two colors with the pipe cleaners as we describe some of our necks. The rounded portion where we're going to connect to the glenoid cavity of the scapula is the head, so humeral head. The necks, there's two different types of necks. When I go around with the pink one just underneath the head, this is called the anatomical neck. The green one is referring to the surgical neck. So two types of necks, anatomical, surgical. The reason we call it surgical is this is right at the region called the metaphysis, where we have the epiphyseal plate or the growth plate. So if we have damage or we break or fracture the bone here, it could end up in surgery. So two necks to learn there. Now as we move on to the rest of the bone, I'm showing you a right. Remember we said this is the head. When I look anterior, this projection on the anterior side is the lesser tubercle. Lesser tubercle. On the lateral side, this big one here is greater tubercle. Greater tubercle. Because of those two tubercles, I have a space in between called the inner tubercular groove or inner tubercular sulcus. So lesser tubercle is more anterior, greater tubercle is more lateral, and then I have that sulcus or groove in between. As I come down the shaft, it'll bow here more on the lateral side, and it'll get rough, and that rough portion is for the deltoid muscle. So we call this the deltoid tuberosity. So where it becomes rough and creates somewhat of a bow here, this is called the deltoid tuberosity. As we come down to the distal end, we're learning condyles. And there's four here. 1, 2, 3, and 4. So 4 condyles. As we learn this, these are 2 epicondyles. Epicondyles towards the edge. On this side, this is the lateral epicondyle. The bigger one from here over, this is the medial epicondyle. Medial epicondyle, lateral epicondyle, and then the two specific condyles in between. The first one that's rounded like a cap. To me, I remember like a baseball cap, and the word cap is in capitulum. So capitulum, capitulum. And then from here to here, all of this is called the trochlea. And students will always say it looks like 2, but it's all 1 because it grooves down and turns, and it looks like it's 2. But all of this is trochlea. And we use that to hinge my ulna inside there. So we'll come back to the ulna, but in review, lateral epicondyle, medial epicondyle, capitulum, and then all of this is trochlea. Trochlea. 2 fossas to learn, one on front, one on back. So on the anterior side, coronoid fossa, coronoid. and we learned coracoid process of the scapula, so it gets a little crazy. On the anterior side, coronoid fossa. Posterior, the larger one, is the olecranon fossa. Olecranon fossa. Right or left with this, I know all of these condyles have to be anterior. So if these are anterior, I need the smooth side of my humeral head to go into my body on the medial side. So I use this to connect to my scapula. So this is a right. If I put this over here on my left side, now I have this rough greater tubercle that's going to hurt when it moves. So this is a right humerus. So then we look at a ulna, my elbow bone. Remember, we said we're taking this and connecting into the trochlea. How do we do that? It's through this C here called the trochlear notch, often called semilunar notch because it's a half moon. So trochlear notch because it hinges inside the trochlea. And how does it do that? Through these two processes. The top one, which is essentially my elbow, the olecranon process, is that projection on the posterior side. On the anterior side, we have the coronoid process. Coronoid process, olecranon process. So the two processes go into my two fossas. My olecranon process is going into my olecranon fossa. My coronoid process is going into my coronoid fossa. So they connect together. As I follow the coronoid process of the ulna, to me it looks like it kind of breaks open here. So all of a sudden there's this little ridge here to where it's like a nice circle, and then it breaks. It doesn't literally break, but I just imagine that. And that point there is called the radial notch because I'm going to use that to attach the radial head. So the radial head goes in the radial notch of the ulna, and that'll help me with right or left. So radial notch. As I come down, the rough projection going more distal. This is the ulnar tuberosity. So ulnar tuberosity. Further distal, ulnar head is the rounder portion. Ulnar head, and then the styloid process, ulnar styloid process. Now this is another styloid process you learned. You learned it on the temporal bone as well. So ulnar head, ulnar styloid process. How do I do right or left with this? I said this is the radial notch, so I attached the radius for this. In anatomical position, we said my radius is my rad bone on my lateral side. In anatomical position, my peaky side is my ulnar bone. So if this has to be on the medial side, if I put it on the left, I can't connect my radius because the radial notch is on the wrong side. If I put this on my right side, now I can connect my radius. So this is a right ulna. So if we add to that, here's my radius. The head switch. So now I have the head on the proximal side. So the round head, radial head. As I come distal, this is on the anterior side. This is called the radial tuberosity. So this bulge, radial tuberosity. And that's how I connect my biceps brachii. It inserts at the radial tuberosity. So radial tuberosity, as I come down to the distal side, the furthest projection, that bump there is the radial styloid process. So another styloid process, and I imagine this kind of looks like my thumb when I place this out. So I use styloid process, and then on this side, on the medial side, I have another groove here, and that's called the ulnar notch. Ulnar notch. And why do I have an ulnar notch? To connect my ulnar head. So as I look at this, I'm using my radial head to connect to my radial notch of the ulna. I'm using my ulnar head to connect to my ulnar notch of the radius. So my heads and notches go together. So we're determining right or left with this. As I come down, I said my radial tuberosity is anterior. So I have to keep this anterior. And I just remember, again, this kind of looks like my thumb in anatomical position. This would stay on the anterior side. So this is a right. If I put this on my left side, my styloid process is going the wrong way. So this is a right radius. So here's a quick review. We did manubrium, body, xiphoid process. We learned that our clavicle has two ends, a acromial end and a sternal end. We learned that our scapula has three borders to it, a lateral border, a medial border, superior border, the main projections, coracoid process. On the posterior side, acromion process. I have a glenoid cavity with the supraglenoid tubercle, infraglenoid tubercle to connect to my humerus. And we said our humerus, as I come down, has a lesser tubercle, a greater tubercle with the inner trabecular groove, deltoid tuberosity, and my condyles, epicondyles, lateral, medial, capitulum, trochlea. When I look at my ulna, we said my two processes, olecranon process, coronoid process, trochlear notch, radial notch. As I come down, ulnar head, ulnar styloid process, and to the radius, radial head, radial tuberosity. As I get to the distal side, radial styloid process, and ulnar notch. So this completes as we get down to the arm. You can review the video on hands and feet once we get past the ulna and radius. We're covering the rest of the appendicular skeletal system, so we'll work through the coxal bone and down to the lower leg. We'll stop before we get to the feet because I did a previous video on hands and feet together. So let's start with the coxal bone. The coxal bone or hip bone is a collection of three bones. So I'm going to divide it into three bones. From my green pipe cleaner up, this is all the ilium. So ilium. And then as I go to the posterior side, what I sit on from here over, this is the ischium, and I have a little piece of tape there to designate where the ischium ends. All of this is coming over to become the ischium. The anterior part that comes down to my pubic bone or the inguinal area, this is the pubis. So pubis, ischium, ilium. So we're covering three bones and the landmarks of those three bones. To determine right or left, I just use that the medial side of the ilium is going to come to my ear, and the pubic bone is how I talk. So I put this nicely up like I'm talking with it. Hey, Brad, how you doing? Versus when I do it this way, I can't connect it, and then this sticks out awkwardly. So this is a right coxal bone. So as we learn this, right ilium, right pubis, right ischium. So let's start with the ilium and first identify just some of our projections that we see on the anterior side and then the posterior side. So we're learning spines. So directionally, these two are called anterior superior iliac spine, anterior inferior iliac spine, anterior superior, anterior inferior iliac spine. On the posterior side, these two projections. Posterior superior iliac spine, posterior inferior iliac spine. So you're using your directions, anterior and posterior, posterior superior, posterior inferior iliac spine. As I come over the top, and it's rough, but it's sharp on top relative to other landmarks. It's not going to cut me, but it is sharp, and this is a crest. On top is iliac crest. Iliac crest, when I go medial, this is called the iliac fossa. Remember, we're learning this for a reason. We'll put muscles and attach ligaments and tendons here, but the iliacus would fit here. So where I can hear with, this is on the medial side, and this is the iliac fossa. So iliac fossa, iliac crest. As I stay medial, we did iliac fossa, and then we take this whole area and divide it into two halves. The top half is the iliac tuberosity. This whole rough area, iliac tuberosity. The bottom half is called the auricular surface, and we're attaching the sacrum there. So on the posterior side, staying medial, iliac tuberosity, auricular surface. As I go underneath that, this projection on the posterior side is called the greater sciatic notch. Greater sciatic notch. So we have the ilium. As I go posterior to the ischium, this is the ischial tuberosity. So this whole region here, ischial tuberosity, and this is what I sit on, ischial tuberosity. As I come up, I have ischial spine, ischial spine. We did greater sciatic notch for the ilium, but now we can do lesser sciatic notch of the ischium. In between the notches, I have a spine. Greater sciatic notch, lesser sciatic notch, and ischial spine. We have ischial tuberosity as it curves and elongates until I get to my blue tape here. This is the ramus, ischial ramus. Ischial spine, ischial tuberosity. When it curves and elongates, ischial ramus. When I move over to the pubis, it really just has two angles to it. I come down and then over. This is the superior pubic ramus, inferior pubic ramus. So I just determined like this is like a C here, but it's backwards. The top, superior ramus, so superior pubic ramus, inferior pubic ramus. So just those two pieces. On top, I have a tubercle, the pubic tubercle. Pubic tubercle. Then I have my ramus and my ramus on either side. A couple other things to look at is the hole is called the obturator foramens. Remember, foramens are holes. Obturator foramen. We get the nervous system. We'll talk about the obturator nerve that comes down, impacts, and innervates on our adductor magnus muscles. Obturator foraмен's the hole. And then where I connect the femur, this is all the acetabulum. Acetabulum. And the projection inside is called the acetabular fossa. This top region of it is the lateral surface of the acetabulum. So it depends on how you're learning it. A lot of texts where they just covered the whole thing is acetabulum. The fossa is the depression inside. I have the lateral surface on top, and then I have the notch, the acetabular notch here. So this is referring to ilium, pubis, ischium. As we connect the femur, the largest and longest bone in the body, we're using the head of the femur to go into the acetabulum, or the acetabular fossa, right at the lateral surface. So the head of the femur, within the head, I have this little hole or divot here. This is called the fovea or the fovea capitis. So on the head, I have this depression, fovea or fovea capitis. We're going to use that to attach a ligament. Head, and it makes sense that then I have a neck. So just like my body, it truly represents more of a head and then a neck. So around it, so as we turn it and look at the head, now you can see more of the neck. So that's the neck. As I stay posterior, I can see these larger projections called a greater trochanter and a lesser trochanter. Greater trochanter and lesser trochanter. And I see this more on the posterior side. And then what it creates is inner trochanteric crest. In between the two trochanters, I have this ridge called the inner trochanteric crest. Inner trochanteric crest. On the opposite side, the anterior, they call it a line. In between the two trochanters, I have intertrochanteric line. So a line in between the trochanters on the anterior side, a crest in between my greater and lesser trochanter on the posterior side. That's a lot. As I come down the posterior side along the shaft, this line is called the linea aspera. Running down the entire shaft, linea aspera. Linea meaning line, aspera meaning rough. It's a rough line. We use that for muscle attachment. Linea aspera. As I come down to the further distal side, staying anterior, this smooth section is the patellar surface to attach my sesamoid bone, my patella. So patellar surface. And then when I twist it and I look, I have these big notches here that are called condyles. Condyles. Now you need to know medial versus lateral. How do I know which side is my medial? My head has to go in to my acetabulum. So this has to be on the medial side. And it's really no matter where I put it. So if I follow this as medial all the way down, this is the medial condyle. So medial condyle, lateral condyle. Turn it this way, doesn't matter. Look for the head, medial condyle, lateral condyle. In between that, I've got a space, we use that for ligaments for the knee, intercondylar fossa. So intercondylar fossa is the space in between my two condyles. How do I do right or left with this? Remember I said this is medial, and I use all of this to be posterior. My trochanters and my linea aspera have to be posterior. So if I stay posterior, I need this to go into my body. So this is a right femur. So at the head, the neck, my greater trochanter, lesser trochanter. As I come down the shaft, linea aspera to my two condyles, medial condyle, lateral condyle, intercondylar fossa. My two condyles of the femur connect to my next largest bone of the tibia. So condyles match with the condyles. I have this condyle and this condyle. So these big round projections for my two condyles to match with my two condyles. How do I know lateral versus medial? As I come down to the distal end, this projection is called the medial malleolus. So we often say when we feel like the balls on our foot as we get close to our ankle, you're feeling that round projection on the medial side. This is the medial malleolus. Medial malleolus. So if this is medial malleolus and I come all the way up, this is medial condyle. So this is lateral condyle. Medial condyle, lateral condyle. In between it, I have a couple tubercles. They're called lateral and medial tubercle. If this is still medial, the two projections, medial tubercle, lateral tubercle, but it's the tubercles of the intercondylar eminence. So this landmark is called the intercondylar eminence in between my two condyles, intercondylar eminence, and it's created by the two tubercles, medial tubercle and lateral tubercle. As I come anterior to help connect a tendon, this is the tibial tuberosity, tibial tuberosity. So my condyles, tibial tuberosity. As I come down the shaft, it projects and has a crest to it, and it's called the anterior margin. So when you say you hit your shin or kicked your shin, this is the anterior margin of what you're actually hitting. So anterior margin, sometimes you see anterior crest. And then, like I said, when you come down, that most distal portion, medial malleolus. So that's the tibia. And now I'm going to connect my fibula next to it. Before I do that, right or left? We said this is the medial malleolus. So this has to stay medial. And then I just use the tibial tuberosity has to stay anterior. So this would be a right tibia. If I put it on my left side, that medial malleolus is on the wrong side. So this is a right tibia. So now I can match it with my fibula as I come down. When we look at the fibula, we're learning two ends. The rounder one that looks more like a rock to me, use your imagination, but this is rounder, and this is the fibular head. As I come down the shaft to the distal side, I have this curved one that looks more like a spoon to me. Remember when we looked at the clavicle and scapula and the acromion process looks like a spoon? To me, this looks like a spoon as well, and this is the lateral malleolus. Some students will say it looks more like an arrow when I project it. So as I come down, lateral malleolus, and on your lateral side, you can feel that other ball next to your ankle. That's that ball, and that's the lateral malleolus. So I have two ends, fibular head and lateral malleolus. For me, the right or left, I do a couple things. One, this has to project away from my body. So if this is on the side and I follow this to the right, when I turn this, that lateral malleolus is going out away. If I put it on the other side, it's going to stab me into my shoe. What I really use though is a trick to how do you eat with this. If I look inside the lateral malleolus, there's a little spoon here, and this little divot helps me to understand right or left. If I can eat with this, it's the correct way. So if this is my spoon and I'm going to eat food and I scoop it up, yum, 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 yum. This is a right fibula because I can use that spoon to eat with. If I turn this and use it as a left, and here is my spoon, if I try to scoop food, there's no way to hold the food. This is going to fall out this way. So this is incorrect. So if you can eat with it with that spoon on the lateral malleolus, this is a correct way to do it. This is a right fibula. So in quick review, as we do the lower leg, we did our two condyles, medial malleolus, so medial condyle, lateral condyle, intercondylar eminence, tibial tuberosity, anterior margin, and then we covered just the two ends of the fibula, the rounder end, fibular head, the one that looks more like an arrow, or to me a spoon, is the lateral malleolus. So this completes our lower leg bones, and we did a separate video that led into the tarsals, metatarsals, and phalanges of the foot. Today we're covering the classifications of joints by their function, which means their movement. We don't get that function until we structurally put them together. And I did a previous video talking about how we classify them based on their connective tissue. And when we looked at different types of joints, we said we have ligaments that are primarily made up of dense, regular connective tissue, which is part of our connective tissue proper. And then when we get into our supporting is our bone. We put our bones together, and then we have different ways to connect them with cartilage, and we call those cartilaginous joints. They could be connected by hyaline cartilage or fibrous or fibrocartilage. And we tend to call these a symphyses joint or a synchondroses joint when we name them by their vocabulary. So when we look at them, once we structurally put them together, they typically have three movements. And these three movements are synarthrosis, amphiarthrosis, and diarthrosis. In plural, you add an ES to it, so synarthroses, amphiarthroses, and diarthroses. And when we look at this, I just use the acronym or mnemonic for this as S, A, and D, that you're sad that you need to learn all this. But basically, we just put it in three types of movement. Synarthrosis or synarthroses means I have no movement relative to the other types of joints. Joints are two bones coming together as articulations. Amphiarthrosis is I have a little bit of movement, some flexibility towards it. And then diarthroses or diarthrosis is full movement. So synarthrosis, amphiarthrosis, diarthrosis is describing once we put the bones structurally together, what is their function, meaning their movement? And that's our SAD, our SAD. I gave you examples of this when we look at where we cannot move the bones relative to others. Synarthrosis, when we talk about our sutural joints. So we look at sutures as my cranium grows together, the different bones. Remember, we have 8 cranial bones. They're not designed to move. So synarthrosis is a sutural joint, is a good example of how they're not supposed to move. Teeth is another good example. Our teeth are not designed to move. That's a gomphosis joint. So we have different types of joints that are not designed to move, where then we do have a little flexibility. So amphiarthrosis or amphiarthroses, the example I gave you, is in between vertebrae at an intervertebral disc. So the disc of cartilage, which is our fibro or fibrous cartilage, to allow for that shock absorption and compression, but I don't have that much movement towards it. So that's called a symphyses joint by structure, but by movement, it's a amphiarthrosis joint based on how it actually functions. Another example is when we use hyaline cartilage. When I connect my ribs to my sternum, there is movement there to allow that flexibility for inhalation and exhalation, but that's hyaline cartilage, and we call that a synchondroses joint. So when we tend to see cartilage, we will have a little bit of movement. The longer the joint is, the more movement we're going to have. And then lastly, diarthroses, sometimes we refer to these as synovial, and there's different types based on how they move. But anywhere where I have a lot of movement, and this is showing a hip socket, but this is called diarthroses. We will have some articular cartilage here to where we allow for some of that compression and movement to absorb that friction so I can move my hips and my shoulders, hopefully the course of 90 years of my life. But that's made up of hyaline cartilage. And then what we tend to see in a diarthrosis joint is what we call a synovial cavity. And a synovial cavity contains a fluid, and it's a synovial fluid that's produced by a membrane called a synovial membrane. So in a diarthrosis actual joint, we tend to see a little bit of space there to where we include some articular cartilage, but also some space with a fluid that we call synovial fluid. These are three types of joints by movement, which means the function. They function by synarthrosis, amphiarthrosis, and diarthrosis. We're covering shoulder joint ligaments. As we describe how bones come together, which are articulations, we connect them in many cases with ligaments. Remember, when we talk about ligaments, the type of tissue is a connective tissue, and it's specifically dense, regular connective tissue. 4 types of tissue in the body: epithelial, connective, muscle, and nervous. Of our connective, we learned 3 types: connective tissue proper, fluid, and supporting. But our connective tissue proper includes our loose and our dense, and we have dense, regular connective tissue that helps support our tendons and ligaments. Remember, ligaments connect bone to bone. So we're covering ligaments here and describing them at the shoulder of how do we connect some of the landmarks that we learn when we're covering skeletal system. So some of the basic ligaments, and we're using the processes that we learned when we covered the scapula and the clavicle, and it tells you where it's going to. So when we talk about the acromioclavicular, acromia referring to the chromium or chromium process connecting to the clavicle. So I go from the acromion process of the scapula to connect to the clavicle. And this is often referred to as the AC joint because you're describing that connection of the acromion to the clavicle at those 2 sections. Now this one is on top. So I remember that AC, air conditioning, typically comes from the top. So my AC joint is on top, acromioclavicular. And then I take the 2 that are coming from the coracoid process and I just go up. So the first one we're learning is going back to the acromion process. So we call it coracoacromial. So coracoacromial. Coracoacromial connecting from the coracoid process to the acromion process. And then I have 2 sections, again, starting from the coracoid process to the clavicle, 2 pieces here, 1 and 2, 1 and 2, coracoclavicular. So coracoclavicular from the coracoid process of the scapula to the clavicle. As you learn these, you tend to mix up the words. So it's easy to understand if you've learned the landmarks of where they connect. But I just start by remembering AC on top, acromioclavicular. And then as I name my 2 for the coracoid, I start from those and go up. So AC on top, coracoacromial, coracoclavicular. And then last one we'll cover on this as we describe the glenohumeral. And remember, gleno is referring to the glenoid cavity of the scapula, and we're connecting the head of the humerus. So 2 pieces to this as we describe it. We're describing where we connect to give me that. What type of movement or function is that? Remember, we learned our 3 types of functions: synarthrosis, amphiarthrosis, and diarthrosis. This is a diarthrosis movement, so I continuously move. The glenoid cavity inside the scapula is connecting to the head of the humerus by way of the glenohumeral joint. So we're referring to the shoulder joint and how we create these supports for the structures of the bones, and then we cover it with the muscles, and we'll talk about the deltoid later. These are the shoulder joint ligaments. We're covering hip joint ligaments. We are getting into the last part of skeletal system, looking at how we connect bones together, which are articulations. When we cover ligaments, remember this is a type of connective tissue. As I pull up this chart that we've covered previously, we've looked at there's 4 types of tissue in the body: epithelial, connective, muscle, and nervous. And now we're talking about connective tissue. There's 3 types: connective tissue proper, fluid, and supporting. When we look at dense, regular connective tissue, that's what creates our tendons and ligaments. Remember, tendons connect muscle to bone. We're connecting bone to bone. So this is what we're covering today is as we talk about ligaments, dense, regular connective tissue. Remember, it contains specialized cells that make fibers, and those fibers include collagen, elastic, and reticular. And their most abundant are collagen fibers because they give us that tensile strength. So as we look at hip joint ligaments, I'm showing you an anterior view on the left and a posterior view on the right. First, as we describe how we connect the ilium bone to the lumbar vertebrae, we call it iliofemoral. So like our previous videos, the words help to describe the joint where the two bones come together and how we connect them with the ligaments. So iliolumbar, we're connecting my ilium to my femur. On the anterior side, to connect my ilium to my sacrum, anterior sacroiliac. So anterior sacroiliac, which means on the posterior side, we have posterior sacroiliac. Posterior sacroiliac and anterior sacroiliac. As I get down to where we connect, first the sacrum to the ischial tuberosity and then the sacrum to the ischial spine, we use those connections here. So these ligaments, and they cross each other. The one that's anterior and smaller is sacrospinous, again from the sacrum. And as I go posterior to the ischial spine, and when I look at sacrotuberous, it's the bigger one on the posterior side, but I can still see it crossing on the anterior. It's going from the sacrum to the ischial tuberosity, So sacrotuberous and sacrospinous. As we dive into the actual hip joint where we connect the femur to the acetabulum and we're connecting to the coxal bone, then we can see first where I have connections to the pubis, to the femur, pubofemoral. So pubofemoral. As I come up towards the anterior side and going superior, there's actually two iliofemorals. There's a vertical and a horizontal. So if you see those separately, there's two iliofemorals, one that goes vertical and then one goes horizontal relative to each other, but it's connecting the ilium to the femur. So you can see iliofemoral and pubofemoral more on the anterior side. If I go the posterior side, connecting the ischium to the femur, ischiofemoral. So all we're doing is using the names of the landmarks and bones we learned previously and connect them with our dense, regular connective tissue to give me connections from the lumbar to the ilium, and as we describe the rest of the coxal bones connecting to the femur. These are our hip joint ligaments. We're finishing up the skeletal system looking at ligaments. Remember, ligaments are dense, regular connective tissue. We've done this on previous videos. When you look at the hierarchy of connective tissue, 4 types of tissue in the body: epithelial, connective, muscle, and nervous. When we look at connective, 3 types: connective tissue proper, fluid, and supporting. When we look at connective tissue proper, 2 types: loose and dense, based on their fibers. When they're densely packed, we call them dense connective tissue. When we look at tendons and ligaments, it's made up of dense, regular connective tissue. So it's dense, it's regular, meaning uniform. And when we look at the fibers, remember there's 3 types of fibers: collagen, elastic, and reticular. Collagen is our most abundant to give us tensile strength. So where we see tendons and ligaments, ligaments connect bone to bone. That's dense, regular connective tissue. So when we look at the knee now, we're focusing on a lot of the ligaments that are internal, when we see a lot in sports injuries when we rupture things like the anterior cruciate ligament. But we'll start, this is an anterior view on the left and a posterior view on the right. When we first look at the patella, remember our sesamoid bone is mixed in with this tissue here that's connecting down to the tibial tuberosity, and then it goes up to the quadriceps tendon. So on top, it's actually a tendon. On bottom, it's a ligament, because this is muscle to bone, this is bone to bone. So patellar ligament is on the distal side here. So this is patellar ligament to come down to the tibial tuberosity. When we look at either side, they are collaterally put together. This is a right leg, looking at both types. And I know this is a right leg because I see the fibula has to be on my lateral side in anatomical position. So my tibia is on my medial side. So this on the lateral side is called the lateral collateral ligament, as it comes up to both the femur and the fibula. It's also called the fibular collateral ligament, but most refer to it as the LCL, lateral collateral ligament. On the opposite side, the medial side, I see medial collateral ligament because it's connecting from the tibia up to the femur. So it's also called tibial collateral ligament, but in many cases they refer to, again, MCL, medial collateral ligament. So I have my collaterals on my lateral and medial side. When I go internal and I look at how it crosses, the first one that's anterior is anterior cruciate ligament. This is the most well-known of the ones that gets teared in sports injuries. But it'll cross, and cruciate means cross, that I have anterior and then posterior when I look at the posterior side. So I can see the anterior here. I can slightly see the posterior crossing on the other side. So anterior cruciate ligament, and then I have posterior cruciate ligament. Anterior and posterior cruciate ligament, my ACL and my PCL. So those are my ligaments of dense, regular connective tissue. And then in between, I have my meniscus or menisci, and these are our shock absorption pads. These are not dense, regular connective tissue. What type of tissue is it? It's cartilage. So it's our supporting connective tissue. 3 types of cartilage: hyaline, elastic, and fibrous. This is fibro or fibrous cartilage. Remember, our fibrocartilage is more of our compression, shock absorption cartilage. We see that also in intervertebral discs. So when we look at the meniscus, these pads, these are made up of fibrocartilage. And remember, I'm using medial because that's the tibial side versus lateral meniscus, which is my fibula side. So you have 2 types of tissue mixed in here, but to create that overall structural support of the knee, and we described the knee, we had the patella, the fibula, the tibia, and the fibula all coming together to give me that ability to flex and extend the knee. These are the knee joint ligaments. We're covering different types of synovial joints and how they move. In previous videos, we organized our joints based on structure. We can organize them based on fibrous joints and fibrous connective tissue, or cartilaginous joints because they're either hyaline or fibrous or fibrocartilage. And then lastly, synovial joints because they allow a little bit more movement because there is a space called a joint cavity that has a synovial membrane that produces a synovial fluid. So when we look at synovial joints, we can now organize them in 6 ways based on how they move. So here's a graphic of the pictures of the arrows and how they might move, but then examples in the body where we find them. So we first look at a gliding, also known as a plane joint. And a plane joint or gliding joint is referring to when you have flat bones that are together, and they can be slightly curved, but they're the same size. So the bones slide together. So the motion of the joint is small, but it's also constrained by the ligaments with them. And because of that, they can be movements in different ways. So you notice I called them monoaxial or uniaxial, meaning they only move on one plane, but it depends on the ligaments. In some cases, you can have more than one plane or movement with this type of joint. So as I look at a gliding joint, what I'm describing here is the tarsals. So in between our tarsals or my ankle bones, I have this type of movement. I also find them in between my hands. So when I look at my wrists or my carpals, I see them when I look at the clavicle and the acromion ligament. So acromioclavicular ligament, they're the same size. So you have that gliding or plane movement on one axis. When I look at a pivot joint is also on one axis, uni or monoaxial, and it's typically when you have a rounded portion of the bone, so a rounded portion, and it's within a ring that's partially articulated with another bone. And the best example with this is our atlas to our axis, my 2 first cervical vertebrae, my C1 and C2. So you have this projecting process, and we call that the dens or odontoid process of the axis. And that articulates with that inner portion of the atlas. And so it's held by a ligament, but it creates that rotation that we've talked about. So when we say we pivot and change course, we're pivoting as we move our head, and that's considered monoaxial. When I look at hinge and we describe hinge, the best example is the elbow joint. So this is the humerus with the ulnar, And when we look at that ulna side connecting to the humerus, what it's doing is you have one bone that's concave, and then it's adjoining this bone, and it's bending and just creating this one movement. So it's also monoaxial. And this example you'll see is also including with that trochlear notch, if you remember, trochlear notch of the ulna, and it's going within the trochlea of the humerus. You also see this with the knees and the ankles. So that's a hinge. When I look at saddle joint, now we're moving into something that's moving on two planes. In a saddle joint, I use the example we talk about our thumbs. So when we say we have opposable thumbs, when we talk about the movements, opposition, reposition. So in this case, you have the articulation to where you have two bones that fit together, resulting like they're sitting on a saddle, like you're sitting on a horse. And this example we're using is that first carpal to the metacarpal. So you're looking right at the base of the thumb here. So it's ability for the palm to move on two planes with the thumb. So as I look at this, I can have to where I'm going like this or like this. So up, back and forth, side to side. So I have two movements. And we talk about this a lot when we talk about grasping things. So when we describe this, it's like you're sitting on the saddle of a horse. That's why it's called a saddle joint. When we get a condylar is another biaxial, meaning on two planes, and condylar is also referred to as an ellipsoid joint. Ellipsoid, like you're on elliptical. The elliptical machine, and it's concave. What's happening here is you're describing that movement in two different directions. So you have this shallow depression here where one bone is articulating with a rounded structure underneath. And where we see that is in the hand. And as I describe this, we're looking at our carpal bones, and we're looking at the scaphoid, the lunate, and the triquetrum. Remember, so long to pinky, here comes the thumb. So long to scaphoid, lunate, and triquetrum, where it's articulating that point at the distal end of the radius. And where you see that is where you have the movement and bending and straightening of the fingers. So as I can straighten the fingers, and the second move is I can move side to side. So side to side, and I can expand my fingers like this. But as I expand, go side to side. So as you move your hand in that lateral going direction, medial direction. So this is on a biaxial. And then lastly, a ball and socket is where we have like multiple planes. So we call it triaxial. We think about like my shoulder, my hips are good examples. And I'm showing you the connection of the humerus and the glenoid cavity of the scapula, to where you have a ball in a socket, to where it's that shallow portion to where the head sits inside there, and it can move anterior, posterior, medial, lateral, so I can move in multiple directions with the ball and socket. So as we're describing all these synovial joints, we're looking at the movements created by how they're connected, and it's increasing the movement because I'm enveloped in a cavity called a synovial cavity. This is the classification of synovial joints.